Welcome everybody. I'm Sam Alkin and welcome to our Dairy Foods office hours for April 2023. Now, I'm a fermented dairy guy and you give me any dairy-based liquid, milk, whey, rinse water, and I'll figure out a way to ferment it into something, right? But recently, we've been taking some of our products and looking into the potential to turn them into powders, which opens up a whole new avenue for us, but also opens up a whole new issue when it comes to cleaning and sanitization for low moisture foods. And so today, Dr. Abby Snyder, who's an assistant professor in the Department of Food Science here, is going to give us a perspective on the food safety challenges we face when cleaning and sanitizing in dry dairy environments, right? Which is a very important issue. And then we're going to turn to Deputy Commissioner Jennifer Trodden to talk about FDA's Laboratory Flexible Funding Model, or the LFFM, that was leveraged with the infant formula recall last year. And she's going to talk about some of the new initiatives that will complement some of the existing microbial sampling efforts being conducted by the Division of Milk Control and Dairy Services here in New York. And then after that, we'll open it up to a bunch of questions, and then we'll also have the panel here to answer some of those questions. So start thinking about those. I'm going to hand it over to Abby to then begin talking to us about cleaning and sanitization in dry dairy environments. Take it away, Abby.
Okay, yeah, thank you for the intro. So I'm just going to give kind of a brief overview about sanitation in dry facilities, maybe 15 to 20 minutes. And then, as Sam mentioned, we'll take questions as a panel at the end. I'm also happy to follow up offline, so I'll share my email address at the end if there's any of those type of questions too. But just to start with kind of like a 30,000-foot view of the problem, food safety and low moisture food systems has been a topic of interest in our field for, I don't know, maybe 15 years. While historically, maybe these products were perceived as relatively low risk because they don't support the growth of pathogens, there have been major salmonella outbreaks and recalls, such as the one tied to Peanut Corporation of America, that have disabused us of that idea. And so over time, a number of different incidents have kind of widened the lens of relevant products and hazards associated with low moisture foods. And this certainly would include outbreaks of Chronobacter and the recall in infant formula last summer, notable primarily for its impact on the availability of infant formula in the US. And so that's sometimes what I think is an underappreciated aspect about the significance of food safety and low moisture food products is its impact on the supply chain. So with the infant formula example, that facility produced a significant portion of all infant formula in the US. So if they have a recall or halt production, that meaningfully impacts the availability of infant formula. With the PCA example, that company produced peanut butter that was used as an ingredient in many other products. And so their recall ultimately involves something like 200 other companies recalling nearly 4,000 products. So although at first glance, low moisture food safety can seem like kind of a niche topic, in reality, it does cut across a large portion of the food industry because many companies use low moisture food ingredients like milk powders in a variety of different products. And a lot of the kind of academic research on low moisture food safety to date has really focused on the development of processing interventions. So thermal or non-thermal treatments used to treat the product to inactivate pathogens. Definitely important work, not the topic of today. So I think more recently, there have been efforts thinking about reducing cross-contamination through surfaces in these type of environments. And so the primary way we do that is through sanitation. So, imagine if this were your food facility and this is what your equipment looked like at the end of a production day. How do you clean and sanitize those surfaces? In a conventional wet operation, it might look something like this. So it could be a full sanitation shift. You have a staff of folks coming in with hoses and brushes and sprayers full of foaming detergents, and they wash down the equipment and they follow with an aqueous sanitizer. The problem is that in manufacturing environments, which are otherwise dry, you generally try to exclude water whenever possible. And that is because introducing water into these otherwise dry environments can create microbial harborage points and facilitate microbial growth. So there is a net benefit to excluding water from these environments. And there are some manufacturers out there who even refer to this war on water as like an effort to reduce moisture in their facilities. Simultaneously, it is worth acknowledging the important role that water plays in sanitation activities. And so just so we have some shared vocabulary for today, sanitation generally includes two functions, cleaning and sanitizing. The purpose of cleaning is to break down and remove food soils and allergenic residues from surfaces through the use of things like detergents and conventional wet programs. And the purpose of sanitizing is to inactivate any microbes that are left on those surfaces after that. So there's an old adage that you can't sanitize a dirty surface. But for both of those functions, water serves important roles. So it is a vector to remove those food residues or to carry the sanitation chemicals in and out. It is a physical force to dislodge adherent particles, among other things. So how do sites accomplish sanitation in the absence of water? And there are a number of different methods available, each bringing their own set of limitations with them. Perhaps most simply, there is COP, or clean out of place, where the equipment parts can be broken down and taken out of the dry space into a wet wash room and cleaned and sanitized in a COP tank. This is certainly effective, but it is time consuming because it involves a full breakdown, and it's not going to be applicable to all pieces of equipment. So a piece that's very large can't be broken down, can't be taken into that other space. Another method is product push through. So a cheap material or a small amount of product from that next run is sent through the line. And that can be useful in reducing carryover of color or aroma compounds between products. So say you're switching from like a hot cocoa mix to like a coffee creamer mix, product push through could be useful. There are also a variety of dry cleaning or physical removal strategies. Things like brushing and scraping and wiping with rags and pads and towels could be single or multiple use. The use of compressed air or vacuums or dry ice blasting. Dry ice is used to kind of dislodge adherent particles in particular. And then finally, some sanitizers are used in spot treatments primarily with like handheld spray bottles or wipes. Alcohol is a common chemistry that gets used because it is fast evaporating. But how well do some of these methods actually work? It is worth pointing out that a number of these activities are simply the cleaning part, right? Dry physical removal strategies. So without wet sanitizing, how effective are methods like dry brushing or dry scraping at removing food soils and their allergenic residues? And so I'm just going to highlight some findings here to illustrate a few points. The figure here are outcomes. This is actually treatment of surfaces soiled with wheat flour, and the bars are color-coded by cleaning methods, so whether it was brushing or scraping. And the x-axis shows increasing ambient relative humidity. So here it's being reported as the equilibrated water activity of the wheat flour. But notably, milk powder is going to be way more influenced by ambient RH. That lactose content in milk powder makes it much harder to remove at higher RH levels. We did similar work too in fruit powders, also a high sugar concentration. And those end up being so hygroscopic that even just leaving them on surfaces under ambient conditions for extended periods of time leads to increased moisture content and adherence to surfaces and makes them more difficult to remove. So that can come to bear in these low moisture food production facilities where extended run times or long-term production campaigns are used. Anyway, the value that's being reported here is the residual weight of food powder that's left after dry cleaning. And so we use an analytical balance for weight. It's super sensitive. And this gives us the ground truth for how much food powder is left after cleaning. I will say that these surfaces looked clean, right? It is worth acknowledging the role of visual hygiene inspections of food surfaces. And, I think intuitively, if you put wheat flour on a surface and you polish it off with a brush or a rag, you can imagine that those surfaces look shiny and polished and clean. However, the outcomes look less great when you overlay data for other hygiene indicators on top. So these purple points here are results from ATP swabbing of the surfaces. It's a common verification test. And the purple line on the figure is a binary cutoff between passing and failing. And so you'll notice there's high variation in ATP results. It's a limitation of that method. And you'll notice that a number of these sites would pass both visual inspection and ATP testing. But looking at the results for more sensitive tests for general protein swabs or specific allergen residue tests, those results are in the table at the top. You can see that all of these surfaces still had detectable allergenic residues. So we reran these experiments. We varied both the roughness of the coupon surface and the particle size of the milk powder, which we size separated, thinking that a rougher surface coupled with a smaller particle size would result in worse cleaning outcomes. We don't actually see a difference here, and our explanation for that was that it had to do with the relative difference between particle size and surface roughness. So even the smallest particle sizes we tested here are still sitting on top of that surface topology of the roughest surface. And so that is to say, although we didn't see a difference here, rougher surfaces might reduce efficacy in the removal of bacterial cells, which are much, much smaller. And then here I'll just kind of lastly share some work characterizing how physical properties of food residues influence the observed differences in cleaning outcomes too. And so the data on the right, again, is milk powder on stainless steel surfaces, and this is at different relative humidity levels. And under each of those conditions, we look at adhesion and cohesion. So adhesion and cohesion are useful variables in sanitation research because they describe how the residue is going to be removed from the surface. So adhesion is the strength of the attraction between the milk powder and the surface, and cohesion is the strength of the attraction between the particles of milk powder. And so notice the difference in the scales on the y-axis between these two figures, but milk powder is highly cohesive at these increasing water activity levels. But for both adhesion and cohesion, there is kind of a threshold above which both go way up. And so we see the same thing in the fruit powder work. There's this phenomena where above this kind of critical level, this transition occurs. And so it would be important to keep the residues below that level on surfaces in your facility to promote cleanability. And then to kind of highlight the main takeaways from this initial question asking, how well do these dry cleaning strategies work? From the perspective of visually cleaning surfaces, yes, these methods often can give surfaces that appear clean, and that would likely reduce carryover of flavors and colors between runs, which is one of the goals of cleaning. Again, I gave the example of like cocoa mix to coffee creamer. But dry cleaning does not, there's not great evidence to support dry cleaning as useful for allergen removal. So these methods alone don't provide an allergen changeover clean. I will note here too that one of the main people who does work in this space is Lauren Jackson of FDA. And so I'm showing some of her work here too with different surfaces, different methods, different allergen residues, but a similar outcome to ours. And so practically, an intermittent wet wash is often used to provide that allergen changeover clean. And that has some drawbacks for facilities, with this otherwise war on water. Okay, so dry cleaning can work well for the removal of food particulate, but not necessarily allergen residues. How well does it work in the removal of bacterial cells? So a different outcome of interest in sanitation programs. So I'm just gonna summarize some of our unpublished work here briefly. I'll say first E. faecium, so Enterococcus faecium, you might be familiar with it as a surrogate for salmonella in a lot of thermal inactivation studies used in dry foods. But in dry cleaning work, I will say that it is looking like E. faecium doesn't always well approximate salmonella's behavior in terms of removal, and so a different surrogate might be better. And I will say that these dry cleaning physical removal strategies do something to reduce microbial load, but they're not amazing at reducing microbial counts on surfaces. So in general, there's less, sometimes much less than a 1.5 log reduction using these approaches. And a lot of these dry cleaning strategies don't penetrate into recessed niches the same way you would expect fluid or a gaseous antimicrobial to. So that's all to say, a true sanitization step would be very useful in dry food production facilities. And there are a number of different efforts out there to develop novel alternatives for sanitizing in dry environments. In my group, for example, we do some work on superheated steam treatment of surfaces. So superheated steam, to get that, you take saturated steam, you continue to add heat to it at the same pressure. So I've included this phase change diagram here for reference. But I've also provided this visual here on the right that shows the changes in density and energy of water molecules in the liquid state, and then in saturated steam, and then in superheated steam as an example. So usefully showing superheated steam is hard to see with the naked eye. We use different pilot scale units in this work. Two of these are these roll-along units where the superheated steam generator is located in the body of the unit, and one is this backpack unit where the generator is actually in the gun of the unit. The two on the right are produced by a company called MHI, and the one on the left is from Goodway. So I'm not going to present any microbial inactivation data today. It is extremely hot. So if you can get your surfaces that hot, it is going to kill vegetative bacterial pathogens. But what I do want to highlight here are a couple potential drawbacks that I think are relevant to dry dairy facilities in particular. So for one, it is worth noting that something like superheated steam is a sanitizing technology. So it does not replace the need for a cleaning step. Again, that old adage that you can't sanitize a dirty surface certainly holds true, but we wanted to know what would happen if you did have some food residues inadvertently left on a surface or after an incomplete or a poor job of cleaning. And so specifically, we asked whether the superheated steam would burn on the residues to the surface, making it very hard to remove later, and whether or not that would impact the results from an allergen residue test. So there's some reports that those assays are sensitive to processing conditions for the allergen residues. So in terms of burn on, it depends on the type of food residue. On the left here, I have data for both peanut butter and milk powder. So we apply the food, we wipe it off. There's a little bit of residue left, which we treat with superheated steam under increasingly severe conditions. And peanut butter actually is a little easier to remove after superheated steam treatment, but milk powder with all its lactose gets burned on and it is much more difficult to remove. So in either case, didn't affect the allergen residue tests. But again, I think superheated steam, not a replacement for your cleaning step. And if you are a dry dairy facility, you would want to think about the risk of burn on and how you would manage that with something like this. The second drawback for this manual application is the relative range of surface area that you're going to treat with kind of a quick pass of a wand across a surface. So here we're looking at temperature distribution across a surface from like the point across from the nozzle, the point of impingement. And this data is collected again using that backpack unit. The rows represent increasing distances between the nozzle and the surface, and the column are increasing thicknesses of the surface. And this is a time course of 300 seconds. And so you can see the temperature very hot at the center, but dissipates relatively quickly across the 6-inch diameter. And ultimately, what we want to know here is how these treatment conditions correspond to microbial reductions. And at that point of impingement at the center, we obtain substantial reductions very quickly, but it also moderates fairly quickly moving outward from that point. So looking at like the 1.8-inch location, you get a couple log reduction after 2 seconds, which is not terrible, but I think it brings up a more practical challenge in implementation. So as designed, operators would need to be fairly precise in application of this tool. And in my experience, precision is not a characterizing feature of manual sanitation regimes. So improving equipment design and coming up with different novel alternatives would be important. This intersects with cost. So let's say we could improve the design. It would definitely be more expensive. Would it still be commercially viable? And so to answer that question, we are undertaking a willingness to pay study. So we're asking members of the dairy industry how much they would pay for sanitation equipment with different attributes related to efficacy or efficiency or sustainability and so on. And so we're wrapping up data collection on that now. If you want to participate in the study, I can email you the link if you would like to give your feedback. But what I'm hoping this brief overview kind of gives us is just a bit of a framework about dry sanitation as it relates to cleaning and sanitizing. There's definitely more to say. I did not get into monitoring and verification, though I think we'll have some questions there for these programs as well. But I think it's worth acknowledging just kind of the complexity of this as a problem, and the fact that I think we'll need a lot of interdisciplinary tools in order to kind of solve it in a meaningful way. And then just to acknowledge as well, my lab and the collaborators and the sponsors for this work. And I would like to mention, so we have some future plans to do work on the development of risk-based environmental monitoring programs in dry dairy facilities. And we are looking for dairy industry collaborators with kind of a shared interest on that topic. So feel free to reach out via email if that is you, or you could contact anyone in the Dairy Foods Extension Program. I'm sure they'd be able to connect us as well. So with that, I will turn it back over to maybe you, Sam.
Thanks, Abby. There's a lot to think about in that presentation. Yeah, for dry dairy environments and just for anyone doing dry powders, I think. So I'm sure we'll have a bunch of questions coming in from the audience. But first, before we get into those, then I'll invite Deputy Commissioner Jennifer Trodden on board to talk to us about the LFFM, or yeah.
Thank you, Sam. Good afternoon, everyone. Thanks for the opportunity to talk to you about the lab flexible funding model. And this lab flexible funding model was created in 2020 as part of the Food Emergency Response Network, or FERN as we call it. It is an FDA program, so it's administered by, both of those programs are administered by the FDA. And that's the ultimate goal is to integrate our nation's food testing laboratories and provide a robust emergency response coordination framework between the FDA and the state public health officials so that we can swiftly mobilize to protect our nation's most precious consumers. So a little bit more about the structure of the Lab Flexible Funding Model, or LFFM as we call it. It is a cooperative agreement between the FDA and state laboratories with the intention to enhance the capacity and capabilities of state human and animal feed testing laboratories in support of an integrated food safety system, specifically through sample testing in areas of microbiology, chemistry, radiochemistry, and the development of special projects that would support and expand that testing. This program is expected to strengthen FDA's efforts to minimize foodborne exposure and prevent foodborne illness by equipping state laboratories, such as the one that we have, with additional resources to increase sample throughput capacity within our state. And this enhanced proficiency will drive a risk-based and prevention-focused food safety system that both the FDA and our states will utilize and ultimately benefit from. So some of the goals specifically and priorities of this program is to, as I mentioned already, improve human and animal food testing surveillance programs, enhance the network capacity of state laboratories by using sample testing in areas of microchemistry and radiochemistry, expand the national capacity in scientific technology and other areas of interest, accelerate foodborne illness outbreak investigations, ultimately trying to reduce foodborne illnesses and deaths, utilize sampling data generated by these laboratories to remove adulterated food from commerce and really scan what foods that could be in commerce that are considered now high risk, and conduct inspections as a result of that analytical detection and sample data. Develop methods for early identification of emerging issues, monitoring those issues, and ultimately evaluating those initiatives or those issues for future sampling initiatives. So currently the FDA has enrolled or has 40 FDA funded states that are part of this cooperative agreement. 14 of our states actually have 2 or more agencies enrolled in this program, which means that the FDA has 55 state enrolled programs in this particular initiative. They have participated or have allocated funding upward to 24+ million awarded across the United States for all of those 55 state programs that are enlisted or enrolled in the program. They have a variety of different tracks that they're focusing on. For an example, for the microbiological assessment track, they have 4 specific tracks. One of the track focuses on food defense. The other one is on human food product and environmental testing. We have another track for animal food product and environmental testing. And then the last micro track is specifically related to whole genome sequencing. On the chemistry side, they have 3 specific analytical tracks that focus solely on human and animal food product testing. And then on the radiochemistry assessment track, they have only 1 single track for that, specifically focused on food defense. So at the end of the day, how does this all affect all of you that are listening here today? So beginning on July 1st of 2023, and as part of this lab flexible funding model that New York is participating in, a portion of the collected samples of the commodities that we will be testing for the next year will be part of or an expansion of the commodities under the dairy program that we currently test for. So the 3 specific commodities that the FDA has asked us to focus on specifically as it relates to dairy products is ice cream, soft cheeses, and raw milk cheeses. They are still defining what specific products would fall under the soft cheese and the raw milk cheese category. So as soon as additional information is provided to us, we will surely share along with all of you. But currently, for an example, for ice cream and soft cheeses, the current testing is for coliforms only. With this addition under the lab flexible funding model, for ice cream specifically, we would also be picking up samples and testing for Salmonella and Listeria. For soft cheeses, for an example, current testing that we do is for coliforms. So the additional testing under that category would be Listeria. And then for raw milk cheeses, we currently test for Listeria, but with the additional testing under the lab flexible funding model, we would also be analyzing those samples for Salmonella. So this additional sampling will begin beginning on July 1st, as I mentioned already, and will run through June 30th of 2024. I believe additional information was provided to all of you via email, but certainly if you have additional questions, reach out to the team. I believe our Director of Milk Control and Dairy Services and Assistant Director are both on the call today, so feel free to drop any questions that you might have on this program in the chat. We are happy to be part of one of the state agencies that's participating in this program. We believe that it really will have a great impact, not just for our state, but for all states across the United States, to create uniformity and consistency across the lab analytical capacity and technical capability. That's all I have. Thank you, Sam.
Thank you.